In this video, we will provide information about depth perception, which is the fundamental mechanism that enables our brains to perceive the world in 3D. Depth perception refers to the human capacity to perceive distance to objects within the environment through visual cues and sensory perception. This perception has a fundamental role in our ability to perceive the world in 3 dimensions. In this 2D image, the illusion of depth becomes apparent. How does this occur? Well, in fact, several things are occurring, such as the image pattern covering towards the vanishing point, our understanding of architectural elements, the proportion of trees in the foregrounds compared to those in the backgrounds, among other effects. Depth perception is derived from a diverse set of depth cues and is typically categorized in 2 main groups: monocular cues and binocular cues. In this first part, we will explore monocular cues. In other words, these are the depth perceptions that do not depend on seeing with both eyes. If you look with just one eye, you will still experience a sense of depth. In this section of monocular cues, we can begin with the static image cues, such as occlusion, relative size, and shading. In this image, one object is occluding the other. The ball and the box are identical. I merely reverse their position. However, your brain is providing you with a 3D perception indicating which one is in front of the other. The occluded edges at the intersection creates a local depth cue. These edges are known as T-junctions and are generally considered an important cue for depth perception. Shadows also convey information about depth, and we use that all the time. That's why shadows are important in 3D games, especially in virtual reality games. Maybe you can't see the difference, but look at this next video. This video shows someone painting a spider, and the 3D perception of a spider comes to life when the person painting it begins to add shadows, showing the importance of shadows to the perception of depth. Now he's going to start the shadows. Did you see the difference? Perspective drawing is a technique employed in art and design to create the illusion of depth and three-dimensionality in a two-dimensional surface. It replicates the way objects appear to the human eye in the real world, where the objects closer to the viewer appear larger, while those farther away seem smaller. While perspective may seem obvious today, the true development of perspective emerged during the Renaissance in the 14th century. Today, we have a comprehensive understanding of how perspective functions, which is what enables the creation of 3D computer graphics. Because our brain is predisposed to a particular perspective interpretation, we can manipulate it. In this image, our visual system accepts the most probable interpretation, that the monsters are roughly the same size in 3D and are positioned at different distances. However, in this case, the monsters are the same size, yet our brain perceives the first one as smaller. The opposite can also deceive our brains. When we observe people in the Ames room illusion, we perceive a distorted environment with actual people. Despite them appearing to be at the same distance, our brains inform us that one person is much larger than the other. Furthermore, when they change position, the apparent size of the people also changes. Many authors play with this confusion of our depth perception, the most famous being Escher, with many drawings with absurd perspectives. Texture gradients are another significant visual cue for perceiving 3D space. We can also manipulate this cue as shown in the presented image. Typically, we observe patterns on the floor or walls, and they are expected to follow a certain sequence. If you tamper with the sequence elements, a straight line may appear curved. Next, we have motion parallax, which involves cues that result from the motion of objects within the scene and/or the motion of the viewer. A classical example is when you are driving a car in a road and observe the farthest objects moving slowly. You will likely perceive this image in 3D, which is another monocular cue as it doesn't require both eyes to perceive depth. Andy Van Dam, a renowned computer graphics professor, once stated, "If it ain't moving, it ain't 3D." Motion parallax is perceived when a viewer is in motion, but it can also be used to assess relative distance or 3D perception when the viewer is stationary and the object is in motion. Wiggle is another technique that enables the monocular interpretation of 3D from 2D images. In this case, two images are rapidly swapped, and your brain will perceive them in 3D. You can achieve this effect by taking two photos with a slightly horizontal separation and displaying them in the same position while happily switching between them. Once again, motion parallax is a crucial resource used to interpret 3D, but you can manipulate it. In this image, we might encounter difficulties in correctly perceiving the 3D aspect because the 3D woman lacks shading. As a result, it becomes challenging to determine where the woman is spinning clockwise or counterclockwise. To introduce something different, here's an example of chromostereopsis, a visual illusion that occurs when specific colors are placed adjacent to each other. This phenomenon creates the impression of depth within color patterns. This may not be super useful, but again, your brain is interpreting 3D from a 2D image. Okay, now we will explore binocular cues. In this case, the depth perception depends on seeing with both eyes. We'll begin with stereopsis, which is the brain's ability to merge distinct images from both eyes to form a unified binocular image in the brain, resulting in the perception of depth. The discrepancy in these images is a depth cue known as a binocular disparity, allowing us to experience depth through the process of stereovision. It's possible to create convincing illusions on depth solely through changes in disparity. This emphasizes the significance of stereovision as a potent depth cue, making it crucial for applications such as virtual reality. Stereoscopy is the science that deals with stereoscopic effects, a technique capable of simulating the effect of depth perception using our binocular vision. It addresses the fact that each of our human eyes, due to their position on our faces, perceives slightly different images when looking at something. Stereoscopic images may appear to float in space, either in front or behind the surface on which they are presented. In virtual reality, stereoscopic vision plays a crucial role in determining the level of immersion in the system. However, it's essential to consider that displaying separated images from the left and the right eyes require possibly twice as much processing power from the hardware. Let's also discuss the human visual field. Human possesses a slightly over 210 degrees forward-facing horizontal arc within their visual field. The vertical range of the human visual field is approximately 130 degrees. It's important to note that the definition of the visual field excludes considerations of the eye movements. Think of someone looking forward. Binocular vision, which forms the foundation for stereopsis and, subsequently, depth perception, covers approximately 114 degrees horizontally within the human visual field. This is the region where we can effectively manipulate stereoscopic images. Another crucial concept is IPD, which stands for interpupillary distance. While you may encounter various names for this measurement, the term IPD is currently the most commonly used. Essentially, it refers to the distance between the center of your eyes, and each person has a unique IPD. Most modern head-mounted displays provide options to adjust the lens separations to match your eyes spacings. Another term frequently used in stereoscopy is parallax, which refers to the apparent displacement or change in the position of objects within your view. Parallax can be observed when different points of view results in a difference in the images. This variation can occur when you see an object in motion, or you are in motion, or just due to the small difference in the position of your eyes. Now, let's check other crucial aspects of stereo vision. One key element we've already discussed is eye separation, which has a significant impact on versions. When our eyes shift focus from a distant object to a closer one or vice versa, they rotate slightly towards each other. These movements are known as convergence and divergence. We use the term vergence to describe the simultaneous movement of both eyes in opposite directions, which adjusts the relative gaze direction to select one of many possible depth plans for sharp focus, allowing us to achieve and maintain single coherent binocular vision. Another remarkable biological mechanism for perceiving objects at varying distance is our ability to change the shape of the eye lens selectively to focus on the retina. We call this accommodation. However, accommodating in headsets images poses a significant challenge since all images are in the same virtual display plane inside the head-mounted displays. Finding a satisfactory solution to accommodating in head-mounted displays has proven elusive so far. In stereoscopic images, we use certain terms to describe whether an stereoscopic object is in front of, behind, or on the screen. These terms are also applicable to virtual displays in head-mounted devices. When an object appears to be in front of the screen, we refer to it as having a negative parallax. If the object seems to be behind the screen, we call it positive parallax. And when the object is precisely on the screen's plane, we describe it as having zero parallax. You can use the following formula to calculate the parallax value, considering the apparent location of the virtual position you want to see. Be cautious when creating images with negative parallax, as users may not be able to converge their eyes to focus on the image. Here's a list of common challenges that one may encounter when working with stereoscopic images or displays. Accommodation. When working with HMDs or even projection screens, the eye's accommodation to focus on the virtual objects is always the same regardless of the depth of the object. And even the user not realizing it, this is a problem. Parallax motion. This only happens with non-tracked stereoscopic displays, since there is just one point of view. So, head movements will present incorrect points of view images. Vergence. The convergence of the eyes is forced forwards and backwards from the screen. If you do not calculate images properly, this may result in difficulties for the user to adjust their eye vergence. Diplopia. This happens when a person cannot see a clear 3D image of the stereo part, what is called double vision. This is very annoying for the user and usually occurs when you have objects too close to the user. The concept of stereoscopic images involves creating two images, one for each eye, which we refer to as stereo pair. Since the invention of stereoscopy, people have employed various techniques to organize pairs of images. Here's an example of an old stereo pair where you can observe subtle differences between the images. These differences are what will allow you to have a depth or 3D perception. The earliest documented instance of stereoscopic display dates back to 1832, when Sir Charles Whipson invented a binocular device, presented here in the left-hand side, that he positioned a stereo pair, and by using small mirrors, viewers could experience the stereoscopic effect. Moreover, the first stereoscopic movie cameras emerged around the 1890s. These cameras simultaneously capture stereo pairs. In the right-hand side, you can see one of the earliest stereo cameras developed by William Fries Green. Today, recording stereo movies has a kind of similar idea, recording two distinct images. We still need to record the images from 2 points of view, but in this case we record with two synced cameras to guarantee that the images were taken in the same exact moment. The modern camera rigs have also many controls for recording stereoscopic movies, like how to separate or rotate the lens. Now, let's discuss computer-generated images. In computer graphics, to render an image, we rely on a virtual environment model, with geometries, backgrounds, illumination, etc. Additionally, we need to establish a virtual camera as a reference to render the image. The result is a 2D image based on a 3D model, but what you see is a flat picture. Graphic cards have frame buffers to store these images. Typically, there is one front buffer and one back buffer for rendering. The front buffer contains what is currently being displayed, while the back buffer is where new images are drawn. This process is known as double buffering. To create a stereoscopic image, you must render your scene from two distinct viewpoints. It's essential to precisely position your camera viewpoints to generate the corresponding images. In stereoscopy, you have additional frame buffers for rendering and displaying images. In this case, you have a left back and a left front, as well as right back and right front buffers. This is commonly referred to as quad buffering. Naturally, you also require a stereoscopic display to view these images. In addition to positioning your cameras slightly side by side, you also need other specific configurations. One strategy is to employ the toe-in setup, where you rotate both cameras inwards. However, this setup isn't entirely effective when displaying on a flat surface. That's what we usually have. Therefore, the most used approach is to utilize the asymmetric frustum. In this method, you maintain your cameras precisely perpendicular to the virtual screen you wish to render, while creating an asymmetric deformed frustum for both types. Here, on the left-hand side, there is a top view of the distorted frustum, and on the right hand, we can observe the homogeneous perspective matrix used when we need an asymmetric frustum. Sometimes you may not have the resources to create an asymmetric frustum. In such cases, you can crop the rendering image to achieve the same result. You might be wondering how to perform these calculations for your head-mounted display. The good news is that modern game engines and virtual reality libraries or packages already have these calculations integrated and readily available for use, regardless of the type of the device you are using. This makes the life of a virtual reality developer much simpler today, allowing you to focus on other aspects of your application. On the right hand, you can see how Unreal deals with that using the VR Palm, and below, with the XR rig used in the default Unity rig for virtual reality.